Hello friends. So in this lecture we'll discuss about power coupled to a fiber from LED. Okay. In this we'll find out that the amount of power which is going to be coupled by an optical fiber in case of step index optical fiber and graded index optical fiber. So let us start. Suppose we are having an optical source with some active area light is coming out from active area only, so the radius of this area will matter, and with the minimum distance we have connected an optical fiber having core and cladding part. Okay. So this is fiber acceptance angle, the angle in which the fiber is going to accept the light, and this light is lost power. Okay. So and this pattern is source radiance pattern, source radiance pattern. Okay. So the source of brightness is given by B as omega s, where as is area of source and omega s is solid emission angle of source. Solid emission angle of source. Now we can write the coupled power as P is equal to integral of dAs, the limit is omega d omega s b as omega s, where AF is area of fiber and omega f is solid acceptance angle of fiber. Okay. So the area of source is limited by the area of fiber, and the solid emission angle of source is limited by solid acceptance angle of fiber. So we will rewrite this equation of power P 0 to Rm 0 to 2 pi. Okay, so this is about area of fiber. Now 0 to 2 pi 0 to this is the maximum acceptance angle of fiber. So d phi sin theta d theta d phi, and is R d. So we have written this equation by using some previous equations which we are not discussing here, and we note that the for surface angle, Lambertian pattern was defined by b theta phi is equal to v naught. This is also formula which we discussed in some previous video. So we can rewrite this equation. Again, we can rewrite this equation. E is equal to 0 to Rs. Why we have written Rs? Because the area, the radius of source is less than the radius of this Rs. The radius of source is less than A, the radius of core. Okay. So we can replace the radius by the smaller radius to limit the radius 0 to Rs. Then 0 to 2 pi total angle, then 0 to 2 pi we can solve this. 2 pi b naught, and now the new limit, or the old one, cos theta, by replacing this value by this formula of Lambertian pattern, we can write this. Okay, so applying limits. Okay, on further solving this, P is equal to pi v naught 0 Rs 0 to 2 pi sine square theta naught maximum okay. We also know that numerical aperture is nothing but n sine theta naught maximum. For air, n is equal to 1, so we can write it again, pi b naught 0 to Rs 0 to 2 pi na square ds rd. Okay. Now for step index fiber, for step index fiber, Na is independent of theta s and r. Okay, theta and r. So we can write power of LED to step index fiber can be written as, using this above formula and solving this, taking Na constant, pi square r square b naught Na square. Okay, you can easily solve this by solving the integration, and we also know that the formula for Na is n1 under root 2 del. So this can be written as 2 pi square rs square b naught n1 square theta. Okay, so now consider total optical power PS that is emitted from the source of area AS. Now we'll again consider the total optical power by source. source. Again we can write AS, area of source, 0 to 2 pi, 0 to pi by 2. Now this pi by 2 is the maximum acceptance angle of fiber. Again we can write B theta sine theta d theta d phi. Okay, now we are considering a source and the light is coming out in form of hemisphere. So we know the formula for hemisphere, the surface formula of hemisphere is 2 pi RH, and area, this area is AS, which we have written. So on solving we'll get pi r square s 2 pi b naught 0 to pi by 2. Again by applying that Lambertian formula we can write cos theta sine theta d theta, because we have solved for d phi, and we'll get pi square rs square b naught. Okay. So power for LED step index fiber TS n square for RS is less than equal to A. Here RS is the radius of source and A is radius of pore. When the RS is greater than A, then the LED can be written as A by RS square PS. Okay. Now in case of graded index fiber, in case of graded index fiber, we know that the numerical aperture can be written as, using previous formulas, to power half, which is approximately equal to under root 1 minus r by a power alpha when r is less than equal to 1.